Okay, in this video we're going to talk about uses of Green's theorem to calculate line integrals and also to calculate the flux. So the first problem that we have is from your book. It's problem 6.4.196, and it says the following: to use Green's theorem to evaluate the following line integral, where the vector field f of xy is given by y squared minus x squared, the ith component, plus x squared y squared in the jth component. And the region, or the line that we're going to integrate over, is a triangle bounded by y equals 0, x equals 3, and y equal to x. So the first thing which we should do, like any problem, is just try and get an idea for what's going on by drawing a picture of the region. So we'll go ahead and do that really quick. So here's our xy plane. And we know that we're bounded below by this y equals 0 guy. So maybe I get another color here. Y equals 0. And we have y equal to x. Y equal x, and then we have x equal 3. Maybe right in here. That is our x equal 3. Okay, so we're going over this path here. That's this triangle here. Okay, now what we're asked to do is evaluate the line integral over that path, right? So the way that we do this is we use a fact, which is the tangential version of Green's theorem, and we know that says that if I have this over some closed C, then I can write this guy as equal to the double integral over the region contained by the C. So this is our region, and then this is going to be Q of, right, this component here. I take its x derivative, and then I subtract from it the y derivative of the first component, and then I take an integral of that with respect to area. Okay, so let's go ahead and do this for our vector field f that they give us. Right, we know that the qth component of that, or the second component, we're going to take its x derivative. So that will be this guy's x derivative, 2x. We will subtract from that the first guy, take its derivative with respect to y, so 2y. And now we have to decide what order we're going to integrate in. So I'm going to go first with respect to y, and then with respect to x. And if I go first with respect to y, I need to decide where's my y going from. So my y is going from y equals 0 up to y equal x, right? So 0 up to x. And then we have to now look at what x is doing in the other direction. It's coming from 0 here out to 3, right? 0, 3. Okay, now it's an easy problem. Now if we've used, this is our, let me just write this here. So this is, tangential. Version, maybe I didn't spell that right, tangential version of Green's theorem. If you want to look that in your notes or your book. And then let's just quickly evaluate this integral. This is something from like the beginning of the course. You should know how to do this. Let's just evaluate this guy. So that's going to be 2x times y minus y squared. 0 to 3 here, and we will evaluate that from 0 to x. Take the x integral now with respect to x. 0 to 3, putting in these bounds, I get 2x squared minus x squared minus 0, right? Integrating there with respect to x. Now this is just simplifies to an x squared, right? So I'm just integrating 0 up to 3 of x squared dx. Well, we know what that is, right? That's just x to the third over 3. Evaluate between 0 and 3. That's going to be 27 over 3 minus 0, which is 9. Okay? So that is our line integral over that triangle. In the next problem, we're going to use the same vector field and the same triangle oriented counterclockwise, and we're going to find the outward flux of F through the triangle. Okay? Alright, so to do this, we also use Green's theorem, but we will use the divergence part of it, right? The part of it which tells us something about calculating flux, which has to do with first calculating the divergence. So first, let's calculate the divergence. Calculate the divergence of F, or maybe you see this notation in the book, something like that. And that is going to be equal to, let's see, remember F, I'm just going to write it down here so you can kind of follow along with me in case you've forgotten, was y squared minus x squared I plus x squared y squared j. Okay, so the divergence, I just take the derivative of this guy with respect to x, the derivative of that guy with respect to y, I get minus 2x plus 2y. Okay. So there's my divergence, and now I want to calculate the flux. Remember, the flux looks something like this. It's the vector field dotted with some kind of normal over the path with respect to some little arc length here, right, or something like that. And then we will do it over the region contained to the left of the parameterization of the circle, right, to the left of the border of that triangle of the divergence of F. And now we have dA. Okay, so let's fill in the gaps. The divergence we calculated to be minus 2x plus 2y, and we can do the same bounds on the integral as before, right? Because we're just integrating over that area, the triangle, so we can do from 0 up to x and from 0 to 3. Okay? This will be then equal to, just evaluating the interval, 0 to 3, and if I do the inside guy, I get a minus 2xy plus, now this is just going to be y squared divided by 2 times 2, so that's just y squared. Evaluate from 0 to x dx. And then I evaluate this guy, I get what? That's just going to be a minus x squared plus x squared, right? So that's going to be 0 to 3 minus x squared. Respect to x, that's minus x to the third over 3 between 0 and 3, which is a minus 27 over 3 minus 9. Okay, so those are two applications of Green's theorem, and hopefully these examples help you kind of understand how to do similar problems for your homework this week.